everyone, for the next 5 minutes, I'm going to bring you along with me for a small journey in space, searching for our cosmic origins. So most of what we know about space today comes from the light you observe on Earth. And this is the spectrum of visible light that we can see with our human eyes. In practice, if I point my telescope here towards our sun, I'm going to observe something more like this. Because space is not empty. And in between stars and planets out there, there is a lot of interstellar gas and dust. And this material can absorb part of the light that is emitted from space before it reaches us on Earth. And this translates into these vertical black stripes that you see here, that appear very specific position in the spectrum that you may see as like a chemical fingerprint that is left on the spectrum by the gas in our line of sight that helps us to determine its chemical composition. So what happens now if I want to observe something that is much further away than our sun? Obviously, there will be even more material in our line of sight. And this material in space may condense in these giant interstellar clouds here that are so dense that we will basically block all the visible light coming from the background stars. Luckily, the visible light is only a small part of the full electromagnetic spectrum here. So by going from the visible to the infrared light, we will be able to see through these clouds, which is very interesting because these clouds are the birthplace of stars. And when stars form in the universe, this is also where we detect molecules in space. And as an astrochemist, my job is to identify these space molecules. To do so, I'm going to use a radio antenna that delivers me this kind of data where no more beautiful colors anymore, but we do find the black stripes again. To me, this data looks pretty much like a barcode that by scanning, it gives me the exact chemical composition of the gas that is surrounding these newly formed stars here. So now that I have identified these molecules, my job is also to be able to explain how they formed in space. To do so, I don't need a telescope anymore. It's just me sitting in front of my laptop running numerical calculations to simulate chemistry, but in space conditions. So to do so, I need several ingredients. First of all, I need the interstellar gas that I'm representing as these cute atoms floating around. And I need interstellar dust, which is a very important ingredient of space chemistry because it provides a surface on which these atoms can land and meet. It basically acts like a dating app here, where these atoms can just swipe right, meet their loved ones, and if it's working, here we go. We've got a new molecule formed in space. So if you want a more realistic example here, let's talk about water, H2O, a very simple molecule, but as we all know, that is essential for our life. So how do we form water in space? First of all, we need 2 atoms of hydrogen to meet to make an H2 molecule. And then we need 1 atom of oxygen here that this H2 molecule will still to the OH molecule, leaving 1 hydrogen atom alone that can just go around the grain to make more chemical reactions. After a million years or so, your dust grain will end up like this, covered up with molecules. And since it's actually pretty cold out there, everything is frozen into the surface of the dust grain. And so there's just one last ingredient missing for our space chemistry here, that is stars. And when this microscopic ice cubes here will get closer to the stars, the temperature is going to be so high that all this frozen material will be released back into the gas phase. And so now you may be wondering, what is the link between these space molecules here and life on Earth? Well, just ask this guy. If it shows up at some point. Yeah. Meteorites and comets are indeed our best candidates for bringing water to Earth a billion years ago when we were just passing by these clouds of molecules and bringing all of them along with them to other planets. But what about more complex molecules? What about amino acids? So if this name doesn't ring a bell for you, that's fine. I'm not a chemist myself. I usually prefer to see them like this, like the building blocks of life. I just want to draw your attention here on this guy, glycine. This is the simplest of all the amino acids we know on Earth. And in principle, it should also be the easiest one to form in space, right? So let's just take a step back here to see where glycine lies in this picture. Well, what I can tell you is that glycine has been detected on the surface of meteorites and comets, but not in the gas phase in space yet. And this raises fundamental questions here. Where's glycine coming from? Was it found on the comet, in the gas phase? Was it brought to Earth at the same time as water? Well, I cannot tell you the answer today because this is still one of the biggest challenges of astrochemistry. And of course, I would love to be the first one giving this answer, but if only it was that easy, right? Yeah. Thank you for your attention.